Good morning. Today we'll talk about more circuit lower bounds. Again, not general circuit lower bounds for any kind of function, but restricted lower bounds for computing monotone functions by monotone circuits. Okay, so we call a Boolean function monotone if it has this property, which basically means if you change a 0 to a 1 in the input, it cannot make the output go from 1 to 0. It can only make the potentially output change from 0 to 1. So here are some example very simple monotone functions. Majority, the functions that's true if at least half the bits are 1. Of course, if you change a 0 to a 1, that can only make the function more true. And or. Parity is, for example, not in a monotone function because there are plenty of cases where you change a 0 to a 1 in the input, and that changes the output from a 1 to a 0. And here's a family of interesting monotone functions. In these examples, we have some number v, and then n, the number of bits in the input, is v choose 2. And we think of an input as encoding a v vertex graph. So the coordinates are correspond to potential edges in the graph, and the input is 0 or 1 there, indicating whether an edge is absent or present. And then you have, for any of these values v and k, this clique function, cliques of vk, which indicates whether or not the graph contains a k-clique. Okay, so clique v comma 3 is a function which is 1 if the input graph contains a triangle. And of course, adding more edges to a graph cannot delete any triangles, so it's a monotone function. Okay, so that's monotone circuits, and there's a related notion, which is that of monotone. Sorry, that's monotone functions. There's a related notion of monotone circuits. And these are just circuits with and or gates. Oops. And no negation gates. And today, actually, we're going to be proving lower bounds. And we can allow the and or gates to have unbounded fan-in, which is actually only makes the lower bounds better. But if you don't worry about that, don't worry about it, and just imagine the and or gates have fan-in too. And the size of a circuit is just going to be the number of gates, as usual. So one thing that's pretty obvious is that if you have a monotone circuit, it computes a monotone function. Because if your circuit only has and or gates, and then you change an input from a 0 to a 1, it can only make the gates, I say more likely to be true. There's no probability, but you know what I mean, more likely to be true. So the output is more likely to be 1. And on the other hand, the converse is also true. This is pretty easy to prove. Let me call it an exercise. But every monotone function is computed by some monotone circuit. Of course, we know that every function is computed by a circuit. In fact, we know that it's computed by either a CNF or a DNF, and that remains true here. Every monotone function is computable by a monotone CNF or DNF. You can just take the CNF and DNF that computes the monotone function, which will have some negations in it, and then just delete all those negated literals. And that'll still compute the function because of the monotonicity property, and it'll be a monotone CNF or DNF. Okay, you can think about why that's true. Anyway, I'll show you a little example here, and I think it'll be obvious anyway. So for example, let's get a monotone circuit for this clique v comma 3 function, and let's in fact make it a DNF. Right, this is supposed to check if the input graph contains a triangle. Well, it's kind of obvious. This on input x is just the big or over all potential triangles in the graph of the three-way and that triangle is present. So I suppose I should write it like this. These are distinct of xij and xjk and xki. Whatever. Okay, so I'm thinking of the input variables as being indexed by pairs, which refer to potential edges. Okay, so this is literally just going over all the potential triangles in the graph and checking if they're there. Okay, and in general, for this particular function, these things are called the min terms. I imagine you've probably seen this concept before. It's like the minimal set of variables which have the property that if you make those variables 1 in the input, then the function is forced to be 1. Okay, so something like a minimal witness that the function is 1. Okay, and in particular, a way to get a monotone DNF for any monotone function is just OR together all the min terms. Okay, and similarly, you can also you can do a CNF with these max terms. Or conversely, like max term is like the maximal set of bits, which if you set them to 0, forces the function to be 0. Okay. So every monotone function can be computed by a monotone circuit. And it's tempting to think that it's the natural way to compute a monotone function, to use a monotone circuit. Why would you use a negation if you don't need to? So here's a question. This is okay, so this for clique 3 is size order v cubed. You might ask, is there a smaller circuit if you allow negations? And the answer, surprisingly, is yes. You can do it with size n to the 2.38 or so. Oh, sorry, this should say v, which is smaller than v cubed. And if you haven't seen it before, I won't tell you why, but it has something to do with matrix multiplication. So that's a little bit surprising. You would think to yourself, come on, how am I going to check if a graph contains a triangle except by doing this? But there's a crazy way you can do it, and in particular this crazy way involves negations. Now you might ask a more restricted question, well same question, but I don't allow negations. Is there a smaller monotone circuit? And the answer to this one was proven by Razbarov in '85. It's also going to be on your homework. Basically, no. Okay, so on your homework, you'll show that the monotone circuit size for telling if a graph has a triangle is at least omega twiddle of w cubed. So this means, v cubed. This means v cubed divided by some polylog v factors. So it doesn't literally show that this is the best, but it basically shows it's the best. So you need basically cubic size if you're going to use a monotone circuit. Okay, and it doesn't have to be this is against any and or circuit. It doesn't have to be a CNF or a DNF. And in general, actually, Razbarov also showed, this one is not on your homework, but he showed that if you're looking in v-vertex graphs for cliques of size 1/4 ln v, this thing needs monotone circuits of size at least v to the omega log v. Okay, and remember n, the number of bits, is basically v squared. So this is also the same as n to the log n to the omega log n. Okay, and what's cool about that is, this is super polynomial in n, and this is an explicit function. In particular, the associated language is in NP. If we take the language of this over all choices of v, telling if a graph has a clique of size about 1/4 log v. So this is a pretty cool result. I mean, the dream result in all of complexity theory is to take explicit function or language that's in NP and show that it requires super polynomial size circuits. And he showed for a monotone function in NP that it requires super polynomial size monotone circuits. You might say that's pretty cool because you might think that, like, well, if you're trying to do a monotone function, maybe you only need monotone circuits. But it's not clear, I guess, whether that's the case. This thing kind of makes you a little bit suspicious. And we'll see a little bit more about this. But nevertheless, this was heralded as like a pretty awesome, circuit lower bound. I mean, it's pretty, it's a good bound to know. I mean, OK, this restriction to monotone circuits is sort of natural in the context of computing monotone functions. And then after this, people made the results better. So Alone and Bapana in 87 showed that if you look at the clique, with cliques of size v to the 2/3, this needs monotone circuits that are at least 2 to the omega twiddle of v to the 1/3, okay, which is 2 to the omega n to the 1/6. Okay, so that's pretty cool. It's still like a monotone function that's in NP, and now it's like requires truly exponential size. And then Andreev in 85, and then he made it better in 87, gave an explicit monotone language in NP. So it's not one that's like as nice as clique, but it's still some nice language in NP, needing monotone size 2 to the omega n to the 1/3 over log n. Okay, so that made this power a little bit bigger. And that's where we're basically stuck. That's basically the best thing we know along these lines. Harnick and Raz in 2000 got this up to n to the 1/3, like n over log n to the 1/3. So they got an extra power of log to the 2/3 in the exponent, for what that's worth. By the way, we're going to show this result today, but with like a 1/4 here, slightly worse. Now, there's a result along these lines that's both cool and uncool. I mean, so this is a result of Eva Tardish from 87. And she showed there exists a monotone language in P needing monotone size that's exponential. I think it was 1/8 or something. So this is, again, is like the sort of thing that always happens like in our like success stories improving like circuit lower bounds. It's like eventually like the problems for which we can show these cool circuit lower bounds are actually easy problems. So it's unclear if like we're really showing that these problems are hard, or it's just we're really showing that the model, that the restricted model we're working on is weak. But we do what we can. Okay, so as I said, today we're going to take this Andreev function and show a lower bound for it for monotone circuits of size that's like 2 to the n to the 1/4 over some log factors. What I mentioned is lecture 1 in 2017, Norbert Blum showed that Andreev's function, which is monotone, requires just non-monotone circuits, any circuits of size 2 to the omega n to the 1/4 by following the proof that we'll see today and modifying it. But then I also mentioned that it was wrong. So that would have been awesome and proof that P does not equal NP, but unfortunately it was false. But yeah, so you'll see the kinds of arguments he was trying to make, because it's exactly the contents of today's lecture, and then tried to make it better, but it didn't work. Okay, any questions right now?
I'm stuck on the max terms thing. Could you give an example of say you're doing majority 3?
Oh yeah, I always get confused about CNFs and max terms too. I can't keep it in my head, even though it's literally the same as min terms, but inverting 0 and 1. Yeah, like majority of 3. Let's see if we can do this. I'm not at my best today either. I'm feeling kind of ill, so if I cannot pull this off, somebody pull it off for me. Let's see. The max terms are ones that look like 0, 0, star, 0, star, 0, star, 0, 0. Like, wait a minute. No. Yeah, I think so, right? So this should be like, and over these 3 terms, or, x1, x2, x1, x3, x2, x3. That's a CNF. And does it compute majority of 3? It's like saying, well, you need to have at least one of, in the first 2 positions, you need to have at least one in the first and third position. You need to have at least one in the second and third position. In other words, it's not OK to have double zeros here, here, or here. I can never.
That just doesn't make sense.
I know. I don't know why. Like, it's literally, they're literally like dual to each other, CNFs and DNFs. But like, I can't make my brain think about. I can only make it think about DNFs, as you'll see in the upcoming parts of the lecture. Good. So yeah.
What is Dardish's language?
It's sort of a little bit weird. It's about like the Lovaas data function of the input graph. It's like approximately at least something. You know, it's not so easy. Like the fact that it's in P is quite hard. Also, I should mention that like Andreas' function is in NP. It's not known to be NP complete. So like I think it's not known whether or not it's in P. We'll see it later. OK, so the well, Razorov used this method of approximations, but I think it was subsequently in some sense simplified to something called monotone switching lemma. So we have like another kind of switching lemma for monotone functions. And this was kind of proved in 1986 by several people / groups, Gyarfas, Stash, Yukna, and Bergen Ulfberg, who are PhD students of Hostad, the other switching lemma guy. OK, so here it is. Let's see if I can fit it onto the board. OK, so let C be a KCNF. And what is a KCNF? It means that the width is at most k. OK, so every or in the KCNF has at most k literals in it. OK, then there exists an LDNF. OK, so that's the DNF of width at most L. And an exact L plus 1 DNF, which I'll call E. What does this mean? It's basically width exactly L plus 1. OK, so every term in the DNF has exactly L plus 1 literals. With the size of E, this means the size. In other words, the number of terms. I should warn that there's like a lot of parameters and letters in this lecture, so hang in there. At most, k to the L plus 1. Such that C is sandwiched between D and D or E. Okay? And this means like pointwise as functions. Okay, so for all input strings, if you plug them into these 3 functions, you know, this output bit is less than or equal to that output bit is less than or equal to that output bit. So it's sort of like C has been like approximately converted into a DNF, which is a CNF, has been approximately computed into a DNF, into a narrow DNF. Except there's like kind of, you know, it's not like D is less than or equal to C is less than or equal to D. There's this like error DNF on the right side. But this error DNF is like not too big. So again, like in the switching lemma, like the great aspect of this monotone switching lemma is that n, the number of input variables, does not appear anywhere. Okay, so like an exact L+1 DNF could potentially have size as large as n to the L+1, but this one, this error DNF, has size only k to the L+1. Okay, so the CNF has been like approximately switched to a DNF. And I should mention that like, okay, so here k and L are arbitrary. And there's no dependence on n. And finally, this is like my worst board ever, but like, and dual statement for CNFs and DNFs. Okay, so like actually whenever you have like a Boolean function, if you like, which is let's say monotone, if you negate all the inputs and negate the output, you get like a new Boolean function, which is monotone. And like that operation changes CNFs and DNFs. So basically you can like syntactically derive, without even proving anything extra, an analogous statement about switching DNFs to CNFs. But I won't write it, because we don't like CNFs. But it's really just the same. OK, so I will now prove this, switching lemma to you. It's actually quite pleasant and cute. OK, so let's take like a bit of an example. So let's say C is this CNF. I guess like k here is 3. Let me get it right. x2 or x3, and x1 or x2 or x4, and x1 or x4. OK, so that's our input CNFC, which we're trying to like convert to a DNF. There's actually like a naive way to convert a CNF to a DNF. Basically, you like take every way of taking like one variable here, one variable here, one variable here, and them together, and like or all of that together. That's the naive way to do it. But that could potentially give you some size that depends on n, which is what we're trying to avoid. Okay, so here's what you do. You build what I'll call a witness tree, which I don't want to define. But I'll just try to like draw an example, and hopefully you'll get the gist of it. For C, OK, so this is going to be a tree. I'll do the example here, where the nodes are not labeled by anything. The nodes are just points. OK, and the edges are all labeled by variables. And at the first node, you like branch on all the variables in the first clause. x1, x2, x3. OK, and what you should imagine is that we're going to be building a tree, and you're going to be looking at paths down the tree. A path is going to be a sequence of variables. And what you should imagine about the path is like, imagine all of those variables are set to 1, and then ask yourself, how does the overall CNF simplify, imagining those variables along the path are set to 1? And if it simplifies just to 1, then you stop the path. And otherwise, you kind of like branch on what's left of your CNF. So let me try to half write that, half draw it. So a path is like, imagine all these variables set to 1. OK, so here you're like, OK, I'm going to imagine that x1 is set to 1. So like this term is now, clause is now made true. So it kind of goes away. This clause is also made true. So it goes away. This clause is also made true. So it goes away. So in fact, I just stop here, because like the whole thing has been made 1. And like this path is like, it's like a witness that C is 1 if all the variables along that path are 1. But like here for x2, I'm saying, OK, I imagine x2 is 1, so then this clause is 1. And here I'm imagining x2 is 1, so this clause is also 1. I'm imagining x2 is 1, so this clause is still hanging around. So here at this node, I just like branch on everything that's in this clause, which is x1 and x4. Okay, and so now like let's take a look at this path. This one is done. This path, x2 is 1. You're thinking x2 is 1, x1 is 1. And like now, when x2 and x1 are both 1, like the whole thing is 1. So you stop here. And actually, similarly, on this path where x2 is 1 and x4 is 1, that would make the whole CNF 1. So you stop here. Okay? And so let me just write this. You terminate a path when sort of C becomes 1. Otherwise, you kind of go back here. So this is like the poorly written algorithm of how you build this witness tree, but I hope you get it. So let's finish here. Here we're imagining x3 is 1. So this clause is 1, but this clause is not 1. So you just branch on all three things in this clause. Okay, so it's x1, x2, x4. And I think you'll see what happens here is this is a termination point. This is a termination point. This is still not a termination point. When you're imagining x3 is 1 and x2 is 1, you know, that kills the first two clauses, but you're still here. So you branch again, x1, x4. Okay, and that's it. So this is the witness tree for this CNF. Yeah.
One question about the K and L arbitrary.
Yeah.
Does it mean that we can choose any L and we get an LDNFD?
Yes.
Okay. And so I'm currently not seeing that. Why would we ever choose a large L instead of a small L?
Why would you ever choose a large L instead of a small L? Because this is an exact L plus 1 DNF. So like, it may accept fewer strings. Like, maybe eventually you'll see, but like imagine, let's see.
Maybe a large L would be a small total size DNF because you have more freedom to make really big clauses.
Yeah, but that is not another bound, right? So maybe it will be, but we will not know that it's small.
Let's see.
Yeah, I think you're right that if the width is small, then E accepts more strings.
Yeah, I mean, if the width, I was trying to like give a very vivid example of like how like you could imagine that like E accepts fewer strings in a situation where like L is larger. And I think that does happen, but like I couldn't quickly come up with like a very vivid example, like where I don't know, this was 2 versus 1.
Why do we want that? Why do we want to
Well,
accept that
we kind of think of E as like a kind of an error in this like approximation. So we want this to be like something that's accepting as few strings as we can.
Are we going to count those strings eventually or not?
Yeah.
Oh, so we actually have E explicitly written down, not just some abstract E.
Yes. I mean, yeah. Actually, I think it'll become a little bit clearer after this, although not fully clear until we kind of complete the proof. Like, in some sense, like this proof is like I'm just gonna like hit you with like a bunch of stuff, and you have to like take it on faith that we're gonna come to like a satisfying conclusion at the end. But yeah, in an effort to go like as directly as possible to the conclusion, maybe the motivation will not be there so much. I should mention that this witness tree building thing depends on the order of the clauses. which it's OK. So like the proof will be fine no matter which ordering you choose on the clauses, but it can make a difference. So for example, suppose we built the witness tree for this C, but with the reverse order on the clauses. And actually, it turns out to be quite a bit smaller. So the first thing we do is branch on the first, well, sort of the last clause, so x1 and x4. And now, like, if we're going in this way, once x1 is set to be 1, this is true, so this terminates. And when x4 is set to be 1, this is true, and all we have left is this, x1, x2, x3. But that's it. Then this terminates. Okay? So you can get a different tree depending on what order you do it in, but, well, we're going to be OK with it no matter what the order is. OK, so remember, we're trying to take C and sort of approximate it by a DNF. So the first thing we do is build this tree. And then I can just easily tell you what D and E are going to be. Oh, but let me write down this fact. I'll put it here. Claim for all strings C of x equals 1 if and only if x is consistent with some path. Where consistent is like in this sense, like x has 1s on all the variables down the path. Okay, I think you can hopefully agree that that claim is true. Okay, so how to make D? Well, these L, D, and F, you just OR together all the paths of length at most L. Okay, so that's an L, D, and F, certainly. And what else we need to know about D is that it's sort of less than C. And that's true. Okay, because like basically D just contains some of the paths which force C to be 1, but not all of them. Yeah?
Clarification, are C, D, and E all monotone?
Oh, yeah. Everything is monotone, yeah. Everything is monotone. That's the valid point. Okay, well, paths here are ands, right? Okay, and how to make E? It's kind of similar. You OR together. So like if all the paths were a length at most L, you'd kind of be done. Like you'd have exactly converted it to a DNF of width at most L. There's some paths, maybe L is 2 in this picture. Then D took these paths, but it missed out on these paths. And E is actually just going to be, in this particular case, the OR of this path to here. So you OR together all the partial paths of length exactly L plus 1. Well, partial in the sense that they might stop at an internal node. Maybe they go all the way to the end. But you just take all the paths that reach L plus 1 and they're just cut there. And along the path and OR them together. So this is supposed to be an exact with L plus 1 DNF, according to the theorem, and that's true. And C is supposed to be at most D or E. And that's true, because like now D, OK, that's like some of the paths, the ones at depth at most L. That's some ways C can be made 1. And then for the other ones, if you have a path of length longer than L, then E is basically just cutting it and say, like, you know what, I'll just call the function 1 if it gets to this point. And that's only like an overestimate, if you will, right? I mean, whenever C is 1, there's some path down the tree that's consistent with the input x. And either that path is at length at most L, in which case D will be made true, or if it's at length greater than or equal to L, it'll make E true. Yes?
Do we also care about the path that's less than L, so that we just add like 3 variables into to make it into length of L, such as for the x1 path? For the
up in D, these are paths of length at most L.
oh, for the E.
For E, no, we only take the ones that are of length exactly L plus 1, like L plus 1.
Okay.
Yeah. Here there's only one example of such a thing. But had like L been 1 in this case, which we're allowed, then D would just be x1, and E would be x2 or x3. Oh, sorry. No, sorry. It would be 1, 2. So it would be good. Whoops, that was wrong. X2 and x1, or x2 and x4, or, oh, I got to write all this. x3 and x1, x3 and x2, x3 and x4.
Is it because we want E to be like with a bigger width? We can make E to be like all partial passes of length exactly L.
Yes.
Do we want to?
That'll be an upper bound. I mean,
Yeah, like well, so no, that was also a legit E, right?
let me actually let me take your question in 1 second, but like, let me just end by saying, because we literally have half a line left, E is supposed to be at most in size k to the L plus 1, and that's correct because the tree has branching factor at most k. Because C is a KCNF. Okay, sorry, your question?
Yeah. So if instead of this E, we will take all partial passes of length exactly L, it also
Yes.
works. So C also is less than or equal to D or E.
Yes. I guess the point is we can do that, but then like our result would be even better had we made D smaller by taking only the completed paths of length L minus 1.
Yeah, so then it's coming back to the question, why do we want large L instead of smaller? But okay, sure. Yeah, let's.
We'll eventually see. Yeah, like hold that thought. It's a good question. Okay, so that's the end of this proof of this monotone switching lemma. And again, like, yeah, somehow the great part of it is that like there's no mention of n everywhere, and that relies on everything having bounded width. So now I'm going to sort of apply this switching lemma. Like, remember, we're trying to prove like lower bounds on monotone circuit size. So like big circuits that have like arbitrary depth of ands and ors. And indeed, what we're going to try to do is like go through the gates like one by one in like a bottom-up fashion, and always try to be approximating a gate by a narrow CNF and by a narrow DNF. And you'll see how that monotone switching lemma will help us do that. And as we do it, we'll be collecting up like more and more errors, but we'll hopefully show that we don't like collect up too much error. And at the end, we'll have like a narrow CNF and a DNF that like approximates the overall function, which on one hand will seem very implausible because it's a complicated function approximated by like a narrow CNF or DNF. Now, granted, there will have been errors that have like kind of accumulated. And the error, like the amount of errors, will be somehow proportional to the size of the circuit that we're going against, because we introduce errors like whenever we switch each gate. And so like the argument will say like, well, when you finally compress everything to like a very narrow CNF or DNF, it must have tons of errors because like narrow CNFs and DNFs cannot hopefully be computing this simple function. And therefore, there must have been a lot of gates to begin with because like the number of errors is proportional to the number of gates. That's like a very hand-wavy picture of what's going to happen. Yeah?
So it looks like if you have the same K, like if you have the same CNF and you increase L, then E actually becomes smaller, right? And the statement is not capturing that.
Say again?
If you have the same CNF and you increase L,
Yeah.
so then you take more parts in D and fewer parts in E, right? So in that situation,
Yes.
the number of terms in E should decrease, right? Which is not like captured by this, right? Just trying to make sure that I understand. Because then that would be a motivation to like pick a larger L, right?
Not clear. Wait, is it clear? You're saying like the number of paths of length exactly L?
So you can only have more paths in D and fewer paths in E.
I'm not sure, right? Like if you imagine the L's here, right? Like if L is 1, there's exactly 3 paths. If L is 2, there's like 1, 2, 3, 4, 5 paths. But if L is 3, there's only 2 paths. So it was not like monotonic in L.
Wait, paths in E?
Paths in the tree. Is that what you're talking about?
No, well the tree is the same, right?
Yeah.
L only changes the paths that we're taking in E and D.
Yes.
So isn't it true that if you increase L, then you'll just have more, like only more paths in D and only fewer paths in E?
No, it's not true.
Yeah.
It's not true. Because like, look, I mean, if for this tree, imagine what goes into E if L is 1, 2, or 3. If L is 1, then 3 things go into E. If L is 2, then 5 things go into E. If L is 3, then 2 things go into E. So it's like it neither like always goes up nor always goes down. Yeah. So yeah, I know this is good. I never really thought through all these things very carefully. I mean, I just learned the proof. Okay, so next theorem will be this approximation theorem, which is sort of what you get in a way if you like apply this switching lemma to every gate in a monotone circuit. So, okay, it's quite a long theorem. Fix K and L of your choice. Eventually it'll be wise for you to choose these carefully. Let F be computable by a size S monotone circuit. Okay. Then there exists a KCNF. This is going to be a long theorem statement. There's a KCNF C, an LDNF D. So these are kind of like narrow final C and D, which sort of approximate your overall circuit, albeit with errors. And there also exist these 2 error sets, which are like an exact K plus 1 CNF E sub C, and an exact L plus 1 DNF, which I'll call E sub D. This guy's size is not that big. It's at most S times L to the K plus 1. This guy's size is not that big. It's at most S times K to the L plus 1. Okay, so this is what I was saying before. Like these error sets that kind of accumulate, they're sort of proportional to, at most, the number of gates in the original circuit, such that the following 2 things. C and EC is at most F, which is at most D or ED. So F is sort of sandwiched between C and D, except for these error sets. This like increases this function because it's an OR. This like decreases this function because it's an AND. So far, so nothing. You could just take C to be constantly 0 and D to be constantly 1 or whatever. But also, D is less than or equal to C. So it's kind of like C is I mean, if you ignore these errors, then it's like D is less than or equal to C, and C is less than or equal to D, and so they're all equal, and they're equal to F. But there's these errors up here. Yeah. So that's it. That's what we're going to try to prove. Oh, actually, before I go on with that, let me just mention one thing back here. It's possible here, for example, that D is, in this monotone switching lemma, it's possible that D is empty. In which case, I mean, an empty DNF is treated as being constantly false. And similarly, in the dual statement, it's possible that C, the CNF that you create, is empty, and empty CNF is considered to be true, right? That's the standard convention. Okay, so It's a little bit hard to interpret, but like this is going to be the theorem that we'll prove now. And it's going to be, a structural induction on the gates of the circuit for F. Okay, so for each gate, G, we're going to create some so-called approximating CNFs and DNFs. KCNF, which I'll call C sub G, and an LDNF, which I'll call D sub G, with D sub G at most C sub G. Okay, so like we're going to do that on a gate-by-gate basis, always have one DNF and one CNF, and the DNF will always be at most the CNF. So like the final D and C here will be the DG and CG for the top gate in F. Okay, so the base case is when G is just like an input gate. And in this case, we just take D, G to be CG to be XI. Okay, that's a width 1 CNF and a width 1 DNF, so it qualifies for to be a C, to be a D or a C. Okay, so everything is exactly computed at the base case, of course. Okay, so then there's two cases: the case where G is an AND gate and the case where G is an OR gate. I'm just going to do the AND gate and then say it's the same but dual for the OR gate, which is true. AND gate. So this is an AND G. Okay, and here, if you like, you can just imagine it has fan-in too, but unless I'm mistaken, it works perfectly fine even if you have unbounded fan-in. So let's let H1 through HT be the gates fanning into G. And in this case, like we're given like these approximators, D HI less than or equal to C HI for all I equals 1 to T. Okay, so we have, by induction, like these DNF and CNF approximators for each of the fanning gates. And now we have to build an approximator for the output gate here, G. Okay, and this is an AND gate. So it's sort of obvious. We want to build DG and CG. For one of them, it's like obvious what to do. Which one? CG, yeah, like obviously. We'll let CG just be the AND of the CNF for HI. Okay? And that's sort of like doing the exact right thing in some sense. The best one could possibly imagine. This is still a width K CNF because all these guys are width K CNF. So if you add together a bunch of width K CNFs, you still get a width K CNF. But what are we going to do for the DNF approximator? D sub G. Well, we have to make width L DNF. And we could try to use the width L DNS for the H's, but we don't. We just say, screw them. We're going to just apply the monotone switching lemma to this thing. Okay, so this will just be like switching lemma, if you will, of CG, which, by the way, also pops out an error set, EG, which we'll come back to. So, okay, there's some good news. So DG is indeed an LDNF as it needs to be. And also DG is at most CG as it needs to be in order to complete the induction. Now, in some sense, that's done for the description of how the construction works. We need to verify all these errors, and so we're going to talk about errors introduced at this stage. As I said, if it's an OR gate, then you use the dual statement of this monotone switching lemma. So I'm always going to be only working on one side, but trust me, it's all analogous for the other side. OK, so what I want to study now is quote unquote error. So perhaps some errors have been introduced at this step. And I'll say what I mean by that. By an error, I mean a string x such that all of these approximators were doing the exact right job on x, but now the approximators are not doing the right job on x. So such that dhi of x equals chi of x equals hi of x for all I, but the approximators disagree on x. OK? So this is what I mean by saying that x is an error introduced at this stage. It means that these two things happen. OK? Now, one thing to observe is that all the CNF approximators were exactly right on the h's at x. And CG is just the and of them. And G is just the and of the h's. So what this means is that CG of x actually equals G of x. Okay? These facts imply that CG of x equals G of x. So like, it's not the CNF's fault. It's not that the CNF has made an error. So in particular, the error has to be because dg of x is wrong. And in fact, it's more than that. It's like, it has to be because like dg of x is 0, whereas these two values are 1.
Hi is equal to hi?
It's an assumption. So I define an error to be an x such that this and this. OK? So it's like I'm defining like not just an error, but like an error has been introduced at this gate. So let me just say this, which I said in words. But any such error x makes the EG true. And remember, by the switching lemma, this is like an exact L plus 1 DNF of size at most k to the L plus 1. Because, right, we always know that GG of x is at most CG of x is at most DG or EG of x. That's something that the switching lemma tells us. OK, but as I said, like for this to be true, but this false, it would have to be that this is 0, this is 1, and therefore this is 1. But dg of x is 0, so it must be that eg of x is 1. Okay, so somehow all the errors that were introduced by this switch are covered by a set EG that you can associate to this gate. And somehow these EGs are just going to collect up over all the gates. It takes, like, after I finish this proof, you still have to think about it for like 15 minutes to see like what I'm about to say like makes sense. But somehow like there's not more I can say than just that's all there is to it. Yeah.
I mean, I understand that this is inside the definition, but we don't have it in our induction. That's why like we cannot just associate that error with the gate, because it's not true that for every AND gate we will have that CHI is just equal to HI.
Yeah, I guess what I'm saying here, maybe induction is a bad word, because like I didn't say what the induction hypothesis is, and like in some sense there is no induction hypothesis. So like maybe it's like a bad word. Like it's an inductive construction of just the C's and the D's, or just you can even forget the word induction. Like I'm just describing how to construct all the C's and D's for each gate, which have this property, and I'm merely saying as you go along constructing them, just make this observation at every gate. that if an error, for any error x that's introduced at this gate, where this is the definition of error gets introduced, the set EG that's popped out is made true by that error. Okay, just make that observation for that gate. Like the proof is not complete, but just like hold on to those things, and then like I'm going to complete the proof by basically just saying put all the errors together. Yeah, but I agree with your queasiness in the sense that like.
It seems like there could be no errors, even if there is an error in normal sense, but there is no errors like in that sense. Because of that, would be the assumption that CHI is equal to HI. Like it could be something that like we approximating but not doing the exact right thing, but there is no errors in that sense.
Somehow what's going to happen is like, if you want, don't think about the errors yet. Just think about like, here's the way by which we construct these approximating DGs and CGs for each gate. The end. Now, having constructed finally the D and the C, which are the D and the C for the top gate, we're going to try to prove this. In particular, we're going to have to tell you like where do you get these EC and ED from. And we're going to do this by looking at, for every input string, we're going to ask, like, is it true that every input string x, that like D of x equals C of x equals f of x? If that's true, then we're like, great. For that string x, this equation definitely holds. If for that x, this equation does not hold, then we'll say there must have been some first gate at which this equation failed to hold. And then for that first gate, if it were an AND gate, and there's going to be a dual argument otherwise, if it were an AND gate, then that string, I'm basically completing the proof in words, then that string will make the EG for that gate true. Okay, and so then we just like slap that EG into this ED, and we're like, hey, that string is also cool for this equation, inequality. So yeah, I just said it all in words. Let me say it a little bit in writing. At the end, we have D, F, at most C, F. Of course, this is our final D. This is our final C. And you know, as I said, for some x, no error is introduced at any gate. This implies that C of x equals D of x equals f of x. Or you can, yeah. So like this equation holds. But otherwise, I mean, for other x's, where this equation doesn't hold, you like charge this error to the first gate where it's introduced. You know, the error, approximation error occurs. And you know, if that's AND gate G, well, we know that E sub G on that x is 1. And similarly, if it's an OR gate, then we know that like the E sub G, which is a CNF in this case, is 0. Okay, and so therefore, yeah, we just put all these error sets together. So like C, or CF if you will, and the AND over all G's, which are OR gates, of like EG is at most F, is at most D, or the OR over all G and AND gate of the EG. Okay, and these satisfy all these properties. Like these are all exact L plus 1 DNFs. So the OR of all of them is also an exact L plus 1 DNF, and its size is at most S, because that's the most number of gates, times k to the L plus 1, because that's what the switching lemma spat out. Okay. Good. So we're soldering on here. So we have this theorem in the bag. So the point is, like, now, like, if you want to, as you do on your homework, like prove that, like, detecting a triangle in a graph requires monotone circuits of size almost v cubed, you basically select K and L very thoughtfully, which I leave to you, and then, well, reason about these inequalities. But, like, in all the cases I know, the first step of your reasoning will always be the same. And it's like it's like a slightly weird looking first step, but I tell it to you because we're going to need it. So a typical use of this theorem starts as follows. You say, OK, you select K and L thoughtfully. So then you get this C, and you get this D, and you get this error set, and you get this error set, and these equations hold. And then you divide into two cases. Case 1 is that C is non-empty. Now, like, why this is case 1? Well, it works. OK, so therefore, it contains some clause, at least one, which is on some variable set R of cardinality at most K. Can't deny that. Now, D at most C. That's something we know. And C is at most this OR over the R variables. Because C is like an AND of a bunch of ORs, including this one. So it's less than or equal to just this single OR. It's true. So F is at most, well, D or this E sub D, and D is at most this. So F is at most or sub R or ED. And somehow, in this case, now you study kind of x's that make F true. So you'll say, well, there's like, there's a lot of x's that make F true. And so in particular, they have to make either this guy true or this guy true, because F is at most this on these x's. And you kind of say, well, both of these guys are kind of pathetic. Like, this guy is just the OR of like k things, and k is going to be some smallish quantity. I don't know. It's going to be at most like polylog in the triangle scenario, I think. So like, it can't be that responsible for making a lot of the x's in this set true. So it has to be like on ED to be like mostly doing the job of being true for like most of these x's. But E sub D is also kind of pathetic because it's an exact L plus 1 DNF. So all its terms, like, this is where you're using the lower bound on the width. All of its terms don't accept too much stuff because they have, they're an AND of exactly L plus 1 things. So, in order for this to somehow like be big enough to cover like all these positive inputs, it has to be that the size of ED is big, and therefore S is big. That's how case 1 goes. Case 2 is actually kind of similar. And you're going to say that, like, wait, case 2 is like weirdly asymmetric with case 1, and it's true. Like, this is like totally 100% symmetric between like true and false, but like this division into cases is not symmetric. And it's just by virtue of the fact that like the example functions we're going to apply to it are like kind of asymmetric between 0 and 1. So like the function like contains a triangle. There's a fundamental difference between like 1s and 0s in that problem. So. Okay, so case 2 is that C is empty. In other words, since it's a CNF, it's constantly 1. Okay, and in that case, we just use the lower inequality. So EC is at most F. And then it's going to be similar. You'll just like study like x's that are in F inverse 0. You have like all these inputs x which make f 0. So they also have to be making EC 0. And again, because of EC's width being large, an individual term cannot be doing such a great job of forcing things to 0, because a term is like a big OR. So the only way it can be forcing a lot of things to 0 is if its EC is large, like a big end of these wide terms. OK, and that again is going to imply that S is large. And that's the structure of the proof. And you should use this structure in your homework to handle the triangles. But we're going to do another case. Hopefully we can do it in 15 minutes, which is this Andreas function. OK, so we now all have the tools in place to prove like a lower bound, an exponential lower bound on the size of a monotone circuit computing a particular monotone function, which is in NP. Also, unfortunately, in Andreas' function, there's like 5 parameters, which is horrifying. But, well, we're tough people. We can do it. So let Q be prime. First, I'm going to define the function. Actually, I should write this up here. Q prime D is going to be basically root Q, but not quite. Q over ln Q. So root Q. And N, the number of inputs, is going to be Q squared. OK. And the inputs, which I'll write as A, are thought of as Q by Q 0, 1 matrices. OK? It's going to be a crazy function, by the way. And instead of like literally saying what the function is, f, I'm just going to say what its minterms are. I'll just say, like, here are a bunch of partial assignments, like, matrices with 1s put somewhere. These are all making the function 1. And anything that has like 1s in those places also makes the function 1. And that will define the function. So f's minterms are 1 for each polynomial, capital P, mapping the integers mod q to the integers mod q of degree less than d. OK, so you look over all q to the d many polynomials, like this. And the minterm is, all right, as a superscript p. It basically has a 1 in the I, comma pi place. OK, so you take an arbitrary polynomial like this. You think of the rows of the matrix as being indexed by the elements of ZQ. And in the third row, you put a 1 in the P of 3 spot. And you do that for all the rows. OK, so you'll get some minterm that looks like this, 1, 1 per row, where the placements are governed by these low-degree polynomials. And you're like, those are the minterms. So any input at all for which there exists a polynomial such that A's has 1s in all the places governed by the polynomial, that makes the function 1. Otherwise, the function is not 1. OK, so this is a strange function. We're pretty much going to just use the good old fact we love that 2 polynomials of degree less than d can agree on at most d places. Otherwise, they're identical. Good. So better not erase the theorem statement, nor the typical use. OK, so let's make a few observations about this function. First of all, it's in NP. I mean, the associated family is in NP. So like this function as a language is in NP. Because if I give you a matrix A, you want to know if it makes the function true, like the prover gives you the polynomial P. Okay, that's just like, d coefficients. And then you just check that your input is indeed greater than or equal to the minterm specified by the polynomial the prover gave you. And OK, the number of polynomials p that we care about is q to the d. And there's its degree at most d minus 1, so you just put one coefficient in zq for each position. And therefore, actually there exists monotone circuits. In fact, DNFs basically of size at most q to the d computing f. Okay, 'cause you just like take the OR over all the polynomials, of which there are this many. Okay, I'm not exactly sure how to define size. The AND of these positions. Okay, and what we're going to show is like that's basically the best thing you can do. So this is the theorem, proved I guess probably by Andreev, that monotone circuit size q to the omega d is required. And finally, what is q to the omega d? This is like 2 to the d log q. And then like that's, well, we have d over there. So this is like 2 to the basically n to the 1/4. It's actually better. It's like the log can go in here. OK, well, don't worry about it too much. The point is that it's exponential in a power of n. OK. Any questions? All right, let's do it. Let me erase this approximation theorem. But you have to remember all these facts about ED, like what its size is and what its width is. I'll remind you. OK. So I erased it, but like the first thing I'll do is select K and L. This is what we always have to do. I'll write it over here. So K, turns out the good K is going to be d log q. And L is going to be d minus 1. OK. Then we follow the typical use pattern. So I'm going to do case 1. OK, so in this case, there exists some R, which now is a subset of the variable. So it's like a subset of positions in the matrix. Size at most k, okay, which is d log q. And there exists this DNF E sub d of exact width d, because this is L plus 1. And size at most s times k to the d, such that right now, as I said, we're going to reason about the inputs that make the function 1. So specifically, I'm going to reason about the minterms. So for all the minterms, a superscript p, like going over all the polynomials, they make true either like the OR over R or E sub d. But now, let's count here. There's q to the d of these. And let's ask ourselves, how many of these minterms can this OR be covering? Not that many. Okay? So this OR is like, it can cover all those minterms that have like a 1 in one of the specific k positions, which is having a 1 in a specific position in the matrix is like fixing one value of the polynomial. Right? So this guy makes true at most, the number of degree d minus 1 polynomials taking one fixed value. Well, k times this, one fixed value. And the number of polynomials p such that p of 7 equals 11 is at most q to the d minus 1. Okay, so they're q to the d overall polynomials, but like fixing that the polynomial on input 7 takes value 11, that's if like 7 comma 11 was one of the k guys in R. That removes basically 1 degree of freedom. So like the number of polynomials that have a certain fixed value is at most q to the d minus 1. Okay? Yeah, and then there's k different fixed values, so we have like a times k here. So that's where I sort of said like, okay, so the OR is kind of pathetic at covering these minterms. So basically, I mean, if you look at the parameters, k times q to the d minus 1 is a lot less than q to the d. So basically, the OR has done a terrible job of like helping. We still have like almost q to the d minterms that still need to be making the ED true. But what about the ED? Right? What is the ED? It's no longer up here. So this guy is this is an exact DNF. Okay, so it's like an OR, let's say of size, at most s times k to the d. So it's an OR where every term in it has exactly d monomials. So like this is actually fixing d values of the polynomial. Like to satisfy this term, you have to take on d specific values. And actually it could be worse, right? Because if in a bad situation, like this term has like entries, like more than one entry in a row, which is not helping the min term. So each of these terms, actually, each term of width d covers at most one of these min terms a sub p. Okay, and therefore it must be that there's a lot of terms. So it must be that s times k to the d is greater than or equal to q to the d minus k q to the d minus 1. And k is roughly root k is roughly root q times a log. So this is still like q to the d minus a half, which is still like way smaller than this. So this is at least, I don't know, omega q to the d. Okay, so therefore s is at least omega q over k to the d. But k, again, it's like something like root q. So, we can just push like an omega up here. Okay, and that's the lower bound that we were shooting for. I have 2 minutes to do case 2. Well, let's go for it. If you must leave in 2 minutes, go for it, but I'll go like 2 minutes over. So it would suck to end here. Okay, so case 2 is still up here, right? So we just have that f. We're just going to use the fact that f is at least this EC, which is an exact k plus 1 CNF of size at most s times L to the k plus 1. Okay, so now we're going to collect a lot of, we're going to say that like f has lots of inputs that make it 0. And like EC has to be like 0 on all of those guys, which will force its size to be large. And the way we'll actually find all these zeros for f is to pick them at random. So we're going to pick a random input with each entry probably being 1. 1 minus, this is very carefully chosen, 2d ln q over q. Okay, there's like 2 lines left in the proof. So what I claim is this is pretty much going to be a 0 input for f. It's very unlikely it's not. So to make that claim, I'm going to ask, what is the probability that this thing is 1? OK, so what is the probability that I make this random matrix, that there exists a polynomial, I erased it, but there exists a polynomial which puts 1s in all the spots where f has 1s? Well, I can union bound over all the polynomials, pick up a factor of q to the d. And then, once I have that polynomial, like I have to have a 1 in all of the spots that p would be true. So like all the I comma p of I positions, of which there are q. OK, so it's just this. Okay, that's the probability that like in all the q rows, I have a 1 in exactly the spot that the polynomial is telling me to have a 1. And this is the e to the minus this. The q comes down, the q, OK, et cetera, et cetera. This is at most q to the minus d. OK, I just needed it to be smaller than like 0.1. But anyway, it's super tiny. So if you pick a random input like this, it's practically always going to make f 0. So you practically better make EC always 0 too. But let's look at the probability that EC of A is 0. And I want to claim it's actually, in some sense, not that high. So this EC, it's like an and fan in S times L to the k plus 1 of or of fan in exactly k plus 1. So in order for the random input to make this thing 0, I can union bound over all of these wires being 0. So it's at most S times L to the k plus 1 times the probability that one of the gates at the bottom is made 0. And it's a big or. So the probability that all of these guys would be 0 is very small. It's like 1 minus that. So it's 2d ln q over q to the power of k plus 1. Now the probability that A makes f1 is almost nothing. So A almost surely makes f 0. So this better be close to 1. Sorry, this better be close to, 1. Which means that this upper bound, this thing has to be also close to 1. I mean, it has to be at least, I don't know, 0.9. It has to be at least actually 1 minus this. Anyway, it has to be huge. And now you see we're going to get a lower bound on S. So we get, therefore, that S is at least omega of L times 2d ln q over q to the k plus 1. Because I just divided by L to the k plus 1. And then I assure you, you put in all the parameters. Let me skip it since I went way over. And this is q to the omega d by setting all the parameters. OK, so the parameters are a little hard to fathom, but maybe the outline of the proof makes sense. And you'll get a little bit more experience with it when you do it for triangles on your homework. OK, so I'll see you on Thursday.